Welcome back, everyone, to our continued discussion on algorithm theory behind linear regression. This is probably the most important part of the algorithm theory because we're finally talking about gradient descent. And gradient descent has applications in machine learning beyond linear regression. More importantly, gradient descent is really where we finally bring in the machine part to machine learning. Here is where we can leverage computational power to help solve problems for us. Recall that in the previous lecture, we just figured out a cost function that we wish to minimize. However, taking the cost function derivative and then trying to solve for 0 to get the set of beta coefficients is going to be too difficult to solve directly through an analytical solution, especially when we start considering that we can have multiple features with multiple beta coefficients. Instead, what we're going to do is we're going to describe this cost function through vectorized matrix notation, and then use gradient descent to have a computer figure out the set of beta coefficient values that minimize that cost or loss function. So our main goals are to find the set of beta coefficient values that minimizes that error, which is the cost function or loss function. And we also want to leverage computational power instead of having to manually attempt to analytically solve the derivative, since at a certain point it's really not feasible for us. We can recall that in the previous lecture, we derived this equation, essentially just the derivative of the cost function. What we're doing here is we're taking the partial derivative with respect to every single beta coefficient for k number of features here. You can also recall our data will be in the form of a matrix X with a vector of labels Y. So we previously discussed how I could transform a real data set into matrix notation. Which means what we could also do is, since I need a beta coefficient for each feature, I can express a vector of beta values. That means I can use a gradient to express the derivative of the cost function with respect to each beta. And essentially what we have here is the matrix notation that we're calling this gradient. And that's what that upside down triangle means. It's just the mathematical notation for a gradient, in case you haven't seen it before. But what we can see here is it's holding in matrix notation the partial derivative of the cost function with respect to every single beta coefficient. Sometimes some people describe the gradient as a just multidimensional derivative. That means we can also plug in our equation of the derivative of that loss function with respect to each beta. So I can go back to that equation that we have and simply plug it in for each of those betas. So we already know what this cost function derivative is equal to. We also know we can vectorize our data. I know that I have this matrix X of all my features and the data points there. I have this vector Y with all my known Y labels, and I can organize my beta coefficients as a vector as well. Which means we can split the gradient of the cost function into two parts. Notice here, what I can do is if I take a look at this first part, I can actually multiply that X in to have the sum of Y times X. And then I can also multiply the X, so I have that beta X and then X naught for that sum as well, which essentially allows us to split this up. So notice that this format is actually the exact same thing I have here. I'm just multiplying that X in order to split this out. So this results in the following notation. And now what this allows us to do is calculate the gradient for any set of beta values. In fact, if you take a close look at this, in theory, what we could do is just guess and check beta values and keep searching and guessing until we've minimized this gradient. Because you should note that the beta coefficients are really the only unknown variable here. The other variables are already known from our data metrics of values of X and Y. Now the question arises is, what's the actual best way to guess at the correct beta values that minimize the gradient? Can I leverage the computational power as well as some clever mathematics in order to quickly find the beta coefficients that are going to minimize this gradient? Well, what we're going to do is use gradient descent to computationally search for the coefficients that minimize this gradient. And I think this is best explored by first seeing what a single beta value would look like, and then seeing what a search for 2 beta values would look like. Keep in mind, we can only really visualize single or double beta values. We can no longer express visualizations for really high dimensional beta value search. But again, what we're doing here is just reducing this gradient for the case of just a single feature. That is, you're just looking for one beta coefficient. What would that actually look like if you were to explore? So essentially, given a cost function, j of beta, how can we computationally search for the correct value of beta that minimizes the gradient, or derivative in this case for a single beta, of the cost function? And what would the search process look like for a single beta value? Let's begin by exploring an analogy first. There's a really common mountain analogy for gradient descent. Let's imagine that you decided to go on a hike up a mountain one day, and then you wanted to end your day, you had a great hike, and you want to go off the mountain and reach flat land. Unfortunately for you, a lot of fog has come in, and so you can't actually determine visually where is up and where is down. Instead, you can only feel the slope of the mountain on your feet. How could you actually get to flat land? What we could do is, based off your starting point, determine the slope that your feet are at. And obviously, this is an analogy for the derivative, since the slope is essentially the derivative, or the gradient, in the case of multiple dimensions. So what you'll do is, as you calculate the slope, or derivative, you'll move in that direction if it's negative. And then you'll move proportional to the negative gradient. And then what you can do is, at your next step, go ahead and repeat the process. Calculate the slope your feet are at, and then keep moving in that same direction. Then eventually you can repeat these steps until you realize that your feet are completely flat. That is to say, the gradient or derivative is equal to 0, and now you know that you've reached the minimum, that is the flat land, and you're no longer on this mountain. And this is pretty much exactly what gradient descent does, and it even looks very similar for the case of a single coefficient search. So let's imagine the simplest possible gradient descent, which is just a one-dimensional cost function. That is to say, we only have a single feature and are just looking for a single beta coefficient. Obviously, we could have just used ordinary least squares to solve for this beta coefficient, but instead, let's go ahead and use gradient descent. So what we would do is start off with some beta value. So we choose a starting point, and then we calculate the gradient at that point. And then we're going to step forward proportional to the negative gradient. And that idea of proportionality is actually really important. That means typically, if we have a very steep gradient, we're going to take larger steps. And we're going to end up repeating this step, keep going, and eventually what you're essentially doing is mapping out the gradient. So this orange curve is just the derivative of this cost function. And that's what we want to do computationally, is just take steps along this derivative or along this gradient until what we realize is that eventually we're going to find that the gradient, or in this case the derivative, is equal to 0, and we found the correct beta value that is going to minimize the cost function. So again, all we want to do is just computationally do a search for this beta coefficient that minimizes this derivative or gradient of the cost function. And again, I want to point out the very clever thing that gradient descent is doing in keeping steps proportional to that negative gradient. That means at the start, when you have a very steep gradient, you're going to take larger steps, which allows you to be more computationally efficient. Since you're starting most likely pretty far away from that minimum value, it makes sense to take larger steps at the start in search of that minimum. Then, as you get closer and closer to that minimum value, that is, the gradient is getting closer to 0, that means you're going to have a smaller gradient, which gives you smaller steps. This makes sure that you're not going to accidentally overshoot the minimum and end up going back up this curve on the other side. To further understand this, let's go ahead and visualize this gradient descent in search of 2 beta values. So now we're expanding from 1 dimension to 2 dimensions. And the process is still the same. except now instead of just a derivative, we really have a gradient, that partial derivative for each of those beta coefficients. So we're just going to calculate the gradient at the point, move in a step size proportional to that negative gradient, and keep repeating this until the minimum is found. So if we can imagine we have now two coefficients and we're mapping out the cost function here, we have beta naught and then beta 1, we could eventually get a mapping that looks like this. This is essentially that gradient of the cost function. And keep in mind that we're not actually going to calculate this mapping. Instead, what we do is we just start off with a point. And then we calculate the gradient at that point, move in a step size proportional to that negative gradient, and keep going until eventually we hit that minimum value. And as you may have noticed here, there's usually an issue with 3D plots of trying to actually visualize the gradient descent on this 3D curve. So instead, what you typically see if you're reading this in a book or article on gradient descent is they will just map out the contours of the gradient cost function and visualize it on top of those contours instead of trying to do a 3D plot. So notice here, I now have the contours of that gradient of my cost function in relation to beta naught and beta 1 coefficient values. Which means if I were to just take a look at that contour plot, it would look something like this, which is typically the diagram you see if you're reading up on, for instance, a Wikipedia article on cost functions. So that's where this contour plot comes from. It's just a 2D visualization representation of that curve we just saw. Now, obviously, if you begin to do this for more than just two coefficients, you can no longer really visualize it because we live in a three-dimensional world. So finally, we can now leverage all of our computational power to find that optimal beta coefficient that minimizes that cost function, producing the line of best fit, which means we're finished with the algorithm theory and we're now ready to code out linear regression. I'll see you at the next lecture.